it is a last but not least, last meeting in the summer series of refreshing last meeting in this series of refreshing the skills for practical computation, and today we will focus on observables. So two types of observables. One group related to charge transfer, and second group related to photoluminescence. Let me share. Hello, Amara. Nice to see you connected. Just you already met each other in person, but anyway, it's good. So here. So here is the schedule. So we will start with 3 talks related to the charge transfer. We partially covered it last time, but now we will have a second look with a little bit more rigor and precision, and just get prepared. David will surprise positively everyone. He will show a new code that was not used before. Then we need to move to photoluminescence, but because of the special schedules, we swap a couple of talks. So Sarah, would you be willing and able to speak as number 4 instead of 10? I don't hear, but I hope it is okay. Okay, yeah, thank you. And then we will go to more normal schedule, showing the first some background, and then going to practical aspects of computing photoluminescence. If your slides are yet on the way, you have time to contribute them a little bit later. Okay, so I'm going to stop sharing and make everyone a co-host. So I believe the first presenter is Hadassah, so she needs to be the. Oh, Hadassah, you already have co-host. Okay. So you can go ahead and start sharing screen and give necessary introduction if needed. And go ahead.
Okay. So, or like Dr. Glean said, we'll be looking at the observables of photoluminescence and charge transfer today, starting with charge transfer. One important physics concept related to that is continuity equation. So, for a little context of where we're at, we talked about Redfield electron dynamic calculations last time. We did some calculations with those. One thing you can analyze with that is charge transfer, and we need the continuity equation, which is a description that pretty much tells us charge is conserved. So you've got local area, charge moving around to a large area. Whatever charge there is has to be conserved. One way it generally gets described as the partial derivative of the charge density with respect to time added to the divergence of the current density. To adapt it to our model, we have a we need to look at a couple partial density distributions. So we have here on the bottom left the partial density distribution of our valence band, and on the right, our conduction band on the left, valence band on the right. Some items of note here, you'll see there's an integration with respect to X and Y. To make our analysis simpler, we are just going to be looking across the Z dimensions, since it's easier to do some analysis looking at just with respect to one dimension and time variable. I suppose if you wanted to see how it looked in different dimensions, you could just turn your model around. But for my model, everything was one dimension Z, so it worked out, or the way I expected the charge to transfer was in the Z direction. So That was good. Also, this row here is more like the density matrix that we saw from previous days last week. So from there, once we have this partial density of our conduction band and our valence band, we have the difference of those to get our total charge density. We multiply that by the Coulomb electron charge, I think, and then we get our then we have the charge distribution that we'll put into our continuity equation. So once we have that, we can continue to simplify our equation. Since the current density, which I believe Mira will be talking about next, it's a three-dimensional vector quantity. It has an X, Y, and Z component. Since we've made the choice to focus on the Z components, we can just say, all right, we'll just assume the average current density in the X and Y direction is 0. So when we do that, we can just focus on the Z part. We integrate it. We get this expression for the current density. And from there, we can implement it into mathematical code. So there's a file available on NERSC that was created by Dr. Johan, and for it, you need the energy pop file, the RR file, and backed out just like we did from last week. Basic calculations. As a note, the current version of the file assumes you have 600 time steps. I had to do some manual manipulation to the code itself since I didn't have 600 time steps for the graphics and some of the logic. So just heads up about that if you use this file. But once you do get that going, you have some pretty similar inputs to last week's Redfield dynamic observables for the initial hole, the initial electron, the homolumo, then the Z steps. There's also some in-code calculations. I'm still figuring out where everything says what it is in the code. I think this is where the integration takes place. So once you do that, we do get a similar graph to last week. We get a relaxation. We can also see charge density as a function of time and space. Here on the right, I have the model I was doing using for my research, which is a genus particle with a cadmium selenium and a lead selenium nanocrystal together. But here on the left, our holes are like blue, electrons are yellow. We can have graphs for our charge density, the time derivative of the charge density, and the change in the current, respectively. So this is the graph from earlier, and I think a note here is the time derivative tells us that yes, there's some change taking place at some point in time. There's also another simplified graph which just shows the current density changing as a function of time. And here this line is just added in to say where the charge is 0, so you can see like where it's changing around. So yes, that's my presentation on the continuity equation using it. I'll leave it open to questions. Yeah.
Let's thank Hadessa.
I have a question.
Go ahead.
I know you said you specifically chose the Z direction. Do you know why that is?
The way I set up my model, this year it's oriented with respect to the Z direction. I was specifically exploring just a spatial separation with respect to Z. So I was expecting the charge to, and also previous research I've done shows this charge transfer between going in the Z direction. Does that answer your question?
Yes, it does. Thank you.
And Hadessa, if I'm not wrong, that divergence operator is just applied in the Z direction. So, and code also is working just assuming that you want to have your plot just in the Z direction. It doesn't work for other direction. Otherwise, you should just tweak the code if you want to, for instance, have a model stretch in the Y or X direction.
What was that again in here?
I'm saying that your initial structure for these codes, usually you should have the codes are developed based on this assumption that you want to plot the distribution of the charges just in the Z direction. So if you have a different orientation in your chemical structure, you just need to tweak a little the code. By the way, thank you. I think you didn't get what am I talking about.
I guess, are you saying it looks like what I have in the code is different than what I have for my model?
No. For instance, your model right now is in the Z direction. It's okay, but if it was a stretch in the Y direction, so that was not consistent with the current version of the codes. So that's the only thing that I'm talking about.
Okay.
Maybe why you choose what G direction, why you don't choose an objection, why?
It was just how I chose to separate things. I just decided to separate things in the Z direction, and then it also worked out that that's how these integration things work out.
Why did you decide to see what, why not index and why? Good structure, maybe not straight instead of Z.
I don't know. I just had them spatially oriented with respect to Z. So, and I was just interested in the charge transferring between the two. So it's just how they were set up. I suppose if I set it up in another way, I could just rotate the model as needed for this calculation.
You go a couple slides back for maybe more, a little more. That's before the code. Going. Yeah. Could you go over why you could say that we can drop our X and Y terms?
I think in part, we're focusing on the, we are focusing on the distribution with respect to the Z-axis. So I guess one, we're mainly interested in Z, otherwise I'm not completely sure why the assumptions made that you can just average the current density in the X and Y direction.
For this, I guess, going from your first to the second, one that required those derivatives to be constant. For this to be true, assuming that Jx only depends on X and Jy only depends on Y.
Yeah.
You have any motion of charge in Y and X direction, or it is only in Z?
I guess since there's molecular dynamics going on, it's possible that there's X and Y Z motion, X and Y motion, but maybe it averages out, so it's negligible.
Okay.
So if we take it as an approximation, so that there is a cube or cylinder and things go on in Z direction. So the current density in X and Y do not change over. So there is just the zero.
Okay. That makes sense.
A provocative question toward the second part of today's talks. When the model is mostly emissive, when it is right after it is being excited, at the process when it transfers charge, or like, can you comment? Will your model ever emit light, or something you prevent it from emitting light?
I guess it depends on, well, it's the charge transfers motion of the electrons going from one band to the other. As long as there's some charge transfer occurring, I'd expect there be some emission of light.
So emission is facilitated or suppressed when you're doing the charge transfer,
Facilitated.
or suppressed? Because to recombine, they need immediately to merge together, right? If we don't pull apart from each other. they at least are expected to have low oscillator strengths and be not very easy.
So they're,
If they're physically separated in space,
okay.
there is their ability to recombine and emit light should be otherwise. Okay?
Yeah.
So this is a connection between first and second chapter, and the assessing spectral signals of these nanostructures is indirect measure of charge transfer. Depending on how much charge is being transferred, it is more or less optically.
So more charge transfer means less
It will
optical.
be darker. It will be darker.
Okay.
I was out of the door for a minute. Were there any questions in the chat line? And any more questions for us? If not, let's thank her, I don't know, first, second, or 10 seconds. So next presenter is Amir Keya. Amir, are you on the connection?
Yes, and if you can share the slides, because I do not have a stable connection, I would appreciate it.
Yes. I will, I can. And please remind me when the slides need to be flipped.
Sure. Thank you, Dr. Klin, and thank you, Hadassah. So I'm going to repeat that, just the exact similar method and code to quantify current density. So Hadassah make the life easier for me and cover all theory. So next, please, Dr. Klin. So previous week we covered the ab initio exactly state dynamics based on non-adiabatic coupling. So for my model, if Dr. Killing go to next slide, I have a conjugated polymer, as you can see on the right, next to a acceptor unit. So here, actually, this previous project, the model was actually the interface or the charge transfer was explored in the Z direction. So the bottom actually chemical structure is DPP polymer, and the top one is PCBM acceptor unit. So to quantify the charge transfer, last week we just measured the difference in the middle figure, the difference between the positive and negative charge, and actually define it as dipole, and the derivative of that dipole gave us the current density. So but in this presentation we are going to use another method as Hadassah presented. So Dr. Kinnick, can we go next? We can skip this. I had to delete this one. Yeah, as you can see in the right, the difference between positive and negative charges gave us the dipole, and the derivative of that dipole gave us the current density. So in that project, we use maximum value of this current density to quantify the current density and also characterize the best photovoltaic system with better actually power conversion efficiency. Next, please. So in this presentation, we want to use continuity equation. I don't want to go through that much. Hadassah already fully covered that. So here in this divergence operator, actually we skip the X and Y direction, since the charge transfer is supposed to be done in the Z direction. We have just that operator applied to the current density just in the Z direction to quantify the current density as an integral of that equation. So the parameter G is something that we are looking for. Next, Dr. Kirin. So to run that code, if you go to the MATLAB directory, you can find the charge density on the line 7. As Hadasa mentioned, just need to tweak the minimum and maximum orbitals mentioned in the energy gap. Also, you need to have the RRR file that we review how to calculate that last week. Also, you need the band out file. Next, please. Yeah, if we take a look through the in the left, the yellow color represent the electron and blue represent the holes, and based on the continuity equation for DPP PCBM, we can have the current density as the right figure. Here's the positive value means the electrons move in the positive direction, and the negative value means that electron move in the negative direction actually. And next, please. Here you can again in the right you can see that the amount of the charge transfer at the interface at the different times, the hole which are transferred and the electrons. Next, please. And here, if we just take a look through the absolute value of the current density, also in the next slide, we have the comparison of two methods. Dr. Kenan, can we go next? Yeah, here the top results represent the current density calculated by derivative as a derivative actually of the dipole over the time, and the bottom one is the current density calculated by continuity equation. So for if I want to compare top and bottom, so in time logarithmic time of -1 we have a peak, but the maximum value for these two methods is appeared at different times. So usually we have the same location, same time for the peaks, but the maximum value at different location. In addition to this, I'm not sure, Dr. Kenan, how to interpret that or how you can find any other connection between these two methods. Can you please share also your feedbacks on this plot? Or does it make sense to have a absolute value of the current density when we are using continuity equation?
So if one would make an average over the neighbors, like smoothing function, then this sharp maximum will disappear. So the main amount of charge is transferred at the same time.
Yes, after smoothing data, if we ignore the each moment, yes, that's the point.
Quite encouraging what you're showing. And I would try to find proportionality coefficient and just show them not in different panels, just on the same panel. Find a scaling factor which will make them as close as possible.
Sure. Okay. Yeah, definitely. I will do that. And yeah, that's the last slide. So thank you. If you have any question, I would be happy to answer, if any.
Okay, please join me in thanking Amir. Any questions in the audience?
Yeah, I have one.
Okay, yeah, please go ahead.
So if I understand I guess the general idea is, the assumption is the charge transfer will happen in one direction. That's why you got this one bit in Z. Just out of curiosity, how much more calculation time would it be to simply just have all three? Or what makes it so much more complicated to do all three dimensions?
I didn't get exactly your question. Why we didn't explore a 3D system? This is your question?
Yeah, yep. And I guess the main question is how much more time would it take to do all three?
Yeah, thank you for the question. This is actually something that we are working on right now. So at first, we just develop a periodic model for the polymer and put just one acceptor unit next to it, and also develop the interface in the Z direction. So this is a very idealized periodic model for this kind of bulk heterojunction. But for the project that we are doing right now, we developed the condensed 3D periodic DFT model. So we pack multiple chains and acceptor units, run with force field calculation to reach to the kind of density, experimental density values, a completely packed system. And then we are running non-adiabatic couplings. But for sure, those systems are 5 to 10 times larger in case of number of atoms. So each system, each aspect of that cubic is around 3 nanometer. So they are pretty expensive and challenging models. And we are thinking how to actually quantify the charge transfer for such that 3D systems. For sure, this kind of approximation or idealization will not work for that 3D model. So we need to find another way to visualize or to quantify, actually characterize the charge transfer between the donor and the acceptor unit in the 3D system.
Yeah. Okay. Yeah, that clarified it. Thank you.
Can I add to this discussion?
For sure, please.
So on one hand, 3 comments. First, actual quantum dynamics can be processed independent on the direction of charge transfer. The question is that we raised and Amir supported is about interpreting the pathway of charge transfer when it deviates from single direction. And next talk will partially address this question. But from industrial point of view, most devices do have like one anode and one cathode, or the solar cell or diode have 2 terminals, and the charge transfer in a selected direction is typically much more important. So therefore, analysis of charge transfer in one direction is valid and important, even if the system shows more rich behavior. So it's all an opinion. More questions in the audience? More questions online? Someone is typing. Aaron, would you like, Amir, would you like to read question by Aaron and address?
Sure. Aaron asked to quantify charge transfer, could you project Kohn-Sham orbitals onto the time evolving density? I do not have a certain answer for Aaron, so it should be doable when it comes to your mind for sure. Can you provide more comments and tips, Aaron, if you think it's useful for this project?
It looks like Aaron's question is, in a good sense, provocative. He pushes us towards the next talk. In some sense, what Amir is showing is already projecting Kohn-Sham orbitals onto time evolving density just in one dimension. And the question is, can one go into like 2 or 3 dimensions? Aaron, is your question interpreted correctly?
Yeah, but I think, wouldn't there be like a numerical way to do it where you could like multiply like occupied and unoccupied? I don't know. I'd have to think about it more how to phrase it.
Okay.
But essentially, like, instead of projecting orbitals, projecting charge density in like whatever grid you're using.
Okay, so instead of population of orbitals, write an equation of motion for charge density distribution.
Right.
It is very possible, but it will be much more expensive because amount of grid points for 3-dimensional distribution is substantially bigger than amount of discrete orbitals that we are pursuing.
Right.
We are propagating like 100 orbitals, and there even a humble system has about 1 million grid points, or at least 100,000. So to be different level of numerical complication is about the same output.
Hmm.
But in derived equations, it is very appropriate, and some people write density matrix equation of motion not as matrix in discrete basis, but as a continuous density with two independent indices. So as a method for theory for equation derivation, it's quite popular, but very unpractical. Okay. Are there more comments or questions to Amir? Questions 1, questions 2, questions 3. Let's thank Amir. Sarah, please confirm if you need to depart sharply by 5, or it is approximate deadline.
Hi, Dr. Kuhn. Yes, it is approximate. I can go for the fourth presenter.
Okay, good.
It's
Thank you.
done.
Then I'll stop sharing and ask the presenter number 3, David, to share screen. And his presentation will answer a lot of questions that were posed to previous 2 speakers. So he probably will give credit to Aaron and to Landon.
Aaron and Landon.
Yeah, but this teamwork goes out of box. It goes out of restriction of one dimension and shows some videos about charge transfer in like multi-dimensional charge transfer. Okay, let's go ahead.
So we are looking at generating 2D dynamics in space. So to begin with, we need our input files. So all these files on what right here, the input files we need for the MATLAB code. And then we have a few different files we need to generate them. So we need the part charge files and the trim.sh code. And that code generates the part charge.trim files and the lockpot.trim file. And then we need our concar and the atom.sh code, and that's going to generate these xx1.xyz files. In addition to that, we also need the RRR, the band out, the energy pop, which are the standard that we've been discussing for the last few weeks. And then these 2 MATLAB codes, and then the band out 2D, which is generated by this first MATLAB code. So if we look at how we actually generate these, so here we're generating the .trim files. So if we look at the .trim script, so you would want to copy the part charge files into a separate directory because the script deletes them at the end. So what the script does is it takes the part charge files and converts them into a form that MATLAB can read. So the things to look for here in the red box here, you want your orbital indexes. And in the blue box here is the number of lines to delete from the part charge file, which should be your atom count plus 9. So when you run the script, it'll give you this string here telling you that it's working. So then if you open one of the .trim files, this is what it should look like. So you start out with this line with 3 numbers. Those are grid points that we're going to use. And then everything after that is the orbital data for that band. So if you were to open just the plain part charge, you would see a copy of the postcard above this. That's what we deleted with the script on the previous slide. And then to create the XYZ files that we need to first create a postcard.xyz, which I have detailed how you can do on NERSC. So if you type in modules show paths, it'll give you a list of useful paths, and you're interested in this one that has the VTST scripts in it. And then you can, using that in that directory, there's a postcard to XYZ script that we can use to create the postcard.xyz file. And then you can run the atom.sh script, and it will request that you enter in the atoms in your model. So enter those in, and then it will make XYZ files for each atom. So then if we look at our first of the MATLAB script, which is the trim parts 2 x.m, and there's a few different versions where there's different letters instead of X, there's a Y, there's an A. So this file needs all the .trim files that were generated by the trim.sh script. So you're going to need all the par charge.trims and the lockpot.trim. And all the lockpot.trim is a copy of one of the par charge to get the initial dimensions. So some things you need to work on or modify. You have your HOMO, OMIN, and OMAX like normal. Depending on what band you're looking on, you may have to change the number of zeros here in the par charge. And you will have to modify the several of these lines. This first, the Z equals, the Y equals, the band out equals, the orbital equals, and the index 3, depending on which dimension you're trying to integrate over. And you would have to make the same modifications to this for loop, which is a little farther down. So in this case, we're integrating over the X dimension. And this script will pump out a figure that looks something like this. Now for the second script, which is the another one of these 4 MEQ scripts, you see that we have our standard parameters, the IH, the IE, HOMO, OMIN, OMAX. So you need to enter all those. Then a little further down, you'll find this band out 2D equals load line, and you'll see all these dim 1, dim 2, dim 3. You need to enter those values, and they are those. They are these 3 numbers right here. And another way you can look at them, this is from the workspace on MATLAB from the trim.m script. So it reads it in there as well. Another place you need to change is this line, which is toward the end of a really long for loop. This is what gives you the axis you're interested in. So you can see that I've matched it up to dimension 1 and dimension 3. Because I'm looking at the XZ plane. So then we need to load in our atom coordinate files. So this is all the .xyz's that we generated. So you see in here, we have them where they load and we're loading, and you notice that they all are a atom symbol 1.xyz. So chlorine, carbon, cesium, hydrogen, nitrogen, lead. Another thing to note with where these red boxes are, depending on what plane you're looking at, you will have to change those numbers.
David, where did you generate those XYZ files?
Right here. So we use this atom script makes them.
Oh, okay, sorry.
So you just, this requires the postcard.xyz as an input. And then you would just, when it requests it, you enter in what atoms are in your system.
Yeah,
And
gotcha.
it'll go through and make all the XYZ files we need for that step.
Okay, thank you.
So then further down the line, we need to specify bonds, and you need to do this for every bond type that you're interested in. So I've opened up the for loop for the carbon-hydrogen bond so you can see it, but there's also nitrogen, hydrogen, carbon-carbon, chlorine, lead, any bond type that you're interested in, you would have to do this for. So the major thing here is, once again, depending on what dimensions you're looking at, you would have to change the order of the Z, Y, and X in this box. So here we need to specify the number of states for the conduction band and valence band. So you see we have these numbers right here to specify that. And then you click run and hope that it works. The code takes a long time to run. So if it works somewhat, it needs to be cleaned up. You get a picture of what we're seeing off to the left, but not to the right here. And you can see that we have a contour graph overlaid with my atomic system, where the contour graph is indicating the orbitals, and I'm trying to, this little figure off to the left is trying to indicate what I'm showing. So this is a volume slice of the part charge from VMD. So you see that we have this slice running through the model. And assuming I did it correctly, that should be the slice we're looking at, but I'm not 100% sure I positioned it correctly in VMD. So this is just a snapshot. It actually creates a video. And this was one of my more early attempts. So it has a bit of oddities going on. As you can see, that it appears that the contour graph is actually moving and covering up atoms and uncovering atoms as it goes along. So if we go to the next slide, which is also a video but does not seem to want to play. We can see a little nicer looking one where we have the orbitals moving and the atoms, we can see them the entire time, and you can see that the orbitals seem to be playing around the lead positions. At least what I believe in the lead positions.
So how do you interpret charge transfer in this video?
So video, as the video plays, it's time moving. So you can see that we have the charge. Probably if we this probably is, but I don't know if I can. You can see that the charge is changing here as time goes on. It's going from yellow now to background to blue. And you can see that happening throughout. So the idea is, with this model, we're hoping for charge transfer along basically this column of atoms right here. And with a small amount over on this one. That is the last slide.
Okay, please join me. Thank you, David. So this impressive talk can make everyone speechless, but maybe there are questions
Should have.
I have another question. So, may I?
Yeah, yes, please go ahead.
Yeah, for different initial excitation, we need to repeat that code. So how, in addition to visualization, how we can quantify the charge transfer or other excited state parameters? How we can report that for a paper or something like that? For instance, if you repeat 3 times, we cannot put a movie inside a paper. So how we can report these kinds of results?
So this would be an addition to our standard graphs. In addition, you actually can put videos and supporting information or supplemental information.
Yes, but this could be your main results for such that study, right? Could be pretty expensive.
If you're trying to use this specifically, you would have to use a series of frames. So like this frame, and then this frame, this, then this, then this, then this, and then this. If you wanted to do this specifically in a paper, you would probably have to do a series of frames instead of a video.
Okay.
That was the main result from it.
Why do you need to specify the atomic bonds?
Because that's how they're drawn. So this one, so if you look, this line right here, that's actually specifying the distance, a cutoff distance, and this part right here is specifying to, if it's within that cutoff distance, to plot the bond. So it plots a vector.
Okay, so you're just artificially connecting them together.
Yeah, we're just artificially connected.
In some sort of this script replaces EMD or GMO just at a little lower level. Because when you merge this dynamics of charge with atomistic models, when needs lines depending on the internal distance.
You are changing the 2D plane towards and away from the atom clusters.
You mean?
You are creating that model in the 2D plane. You are moving that plane towards and away from the atoms.
So the plane should be constant about where this orange plane is in the model to the left. My understanding of how it works.
So what is the condition of changing that charge density from right to left?
So it'd be,
Is it due to spatial position of your 2D plane or the?
so we have our 3D model, and we have a slice somewhere through the center somewhere. So blue would be on one side of the slice, yellow would be on the other side of the slice.
So yellow, when you make the yellow, it is towards close to the atom clusters.
It'd be closer to the screen, to the viewer, so it's coming in and out of the screen type of idea, I think.
I'm interpreting the question of the issue a little bit different. Can you go to the slide where you create went out to the. Okay, so I'm requesting the way it was. Great. So here one takes the 3-dimensional charge density as it has been read into script. Select at which value of a certain coordinate you want to make a slice, because plane is just fixing one coordinate and letting others to change, and then calling it to the 2D orbit. But if one wants to redo 2-dimensional dynamics at other slice of the spotting, one needs to change this parameter and do everything. So it's only one slice out of 3-dimensional dynamics. And one can find different results for different ways of chopping the model. Were you asking this?
Yes, so which one we need to choose based? how to.
Well, it's not a question to a program, but it's a question of to the one which generates results. Depending on what you need, you select position of your line. So, okay.
Why do you need a lockbox?
So the lockpot, that's because of how Landon wrote the script. It was designed for lockpots, not for bar charges originally. And we just carried it over. So the way it works is this. So if you look at the script that we generate the bar charge files, the last line of it is literally just copying the last one to lockpot.trim. So they have the same format. So all that's doing is reading in this first line, this 378, 120, 240 line. All that lockpot line in the code is doing is reading that in and determining what dim event is.
So it's just because of header.
Yeah.
It's like inherited from historically. So I don't remember, like 3, 4, 5 years ago, London was undergraduate, which is not a wonder. And he was taking physical chemistry course that you guys have today. And there was a project to look for wave function and wave packet propagation in the multidimensional potential. And London decided to extract potential from ab initio data. And potential in Redfield in the file log code, he needed to just read and wrote. And then several generations of researchers found this core code useful. Like there are maybe a few more later. There was a question from Aaron in the chat line.
Aaron asks, what if bar charts file has non-numeric values such as a bunch of stars? The best way to do this is to hope that it doesn't. Unfortunately, I wasn't that lucky. So at this point, what I've done is copy the previous bar charge to make it work. I need to sit down and regenerate them and figure out how to actually make them where they give me numeric values. And I don't know how to do that because I'm not entirely sure what caused them to not have numeric values.
Aaron, are you satisfied, or you want to give other way to avoid this problem?
Well, I'm not sure how to avoid it, but if it does happen, like generally what I do is there's it's 2 steps. So first there's a Unix command to tell it to search a file for any commands. So if you just tell it to search for stars, and then you can put in another command to tell you which line that those stars are at. Then you can there's like another Unix command where you can jump to that line and just set it to 0.
Okay, so if 1 point out of a million has a spike or error, and we place it to 0, it will be not a big error in the integrated result.
Right. And you'll know if it's there because
I don't
like
know.
MATLAB won't load the file. It'll give an error.
Yeah, it gives a very annoying error.
And there are 2 replaces like SED or
Yeah,
things like
there's a few different versions that you can do to replace this. The grep minus capital FN allows you to search for it. And gives you the line number. So the F allows you to search for the string, and the N gives you line number. That's what the FN option does.
I do have a question. Can you go to the very last slide? So I think Amir was asking about the interpretation of this results, right?
Yeah. Yes, I think it was as well.
Yes.
So I will try to interpret, but David, please correct me. So this model consists of three units. So here are the fragments of thin film, which is as thin as 2 atomic layers, and it interfaces with thin film which is as thick as 5 atomic layers. And this thin film with 2 layers and 5 layers do have different regime of quantum confinement. The gap in thinner is bigger than in thicker. So it is expected that both electron and hole will migrate from a more confined to less confined. And if we try to rerun the dynamics, we will see that charge density disappears in this lower segment and will reappear in the upper segment, at least qualitatively. I mean, does it make sense just as an attempt to interpret?
Yes, of course. Thank you.
More questions, David?
I have one more question. Yeah, can you go to slide number 11, I think? So here, that red rectangular, it's for setting of XZ, right?
That's ZY.
Z, what if you want to change to another plane? For instance, if you want to change to XY plane, how do you change it?
So the Z should be the last one. And whether X or Y should be first depends on how you organize these ones.
Okay.
Depend on how you organize these ones.
I see. Okay, guys, thank you.
There was a question in the room by Joseph.
Can I answer my question? My question was just going to be how we change the numbers for loading the atomic coordinates. But you kind of answered it. It has to be.
So the idea is you got 2 dimensions, so you want, and we're looking at it in 2 dimensions. So the X and the Y, assuming Z is coming out of you on this movie at the end. So let's assume this is Y, this is X, and then Z is coming out. That this first row, that's going to be the X. The second row is going to be the Y. And this third row is going to be the Z. So you need to adjust them based on what your specific system is. So if you want the Z to be the X-axis in the final movie, it should be the first one. If you want X to be the first X-axis, it should be the first one. And X is the 1, 2 is Y, 3 is Z within your molecular system. So if you look at your model and it has a coordinate, those are how they relate.
Last call for questions, David. Question 1, questions 2, question 3. Please join me. Thank you, Jerry Johnson. Now the next speaker is Sarah. So her talk will give practical skills for computing photoluminescence for the models with explicit spin polarization, with unpaired spins. We will, after her talk, we will go back to background and ramp up to this level of development in a little more continuous way. Okay, Sarah, floor is yours.
Thank you, Dr. Keya. Hello, everyone. So I'm going to briefly explain about how to generate the emission spectra for the spin polarized case. So as I talked, previous weeks, in order to run this MATLAB code, we need some files, including the RRR file, bound out, diff, bound out, some energy pop, formaster, and absolutely the MATLAB code. So as I mentioned previous week, we need to modify a bunch of numbers in the MATLAB code. We need to specify the number of HOMO, LUMO, the range of orbital that we want, the number of steps, as well as the cell size in the Z direction, and of course the transition that we are interested in. In this case, we kind of sorted the always strengths file in the, and we are interested in the transitions with the highest oscillator. So after modifying the MATLAB code, if all process goes well with the MATLAB code, we ended up to some plots. So one of them is, as you can see in the left, the energy dissipation as a function of time and as a function of space in the right panel. Also, you can see the relaxation rate for the electron and holes. So electron is kind of showed by the yellowish color, and the hole by the bluish or purplish color. So next and final images or pictures that MATLAB plots for us are these three panels. As you can see from top left, this is the dissipation of excitation energy as a function of time, and also as well as on the top on the right, it is the emission spectra, and also time integrated emission in the below the time integrated emission. So you can see that each peak corresponds for a specific transition. So for my case, the highest intensity for the excitation energy corresponds to the LUMO to HOMO. And also we can modify this range of energy to our desired range of energy with just very simple. We need to just modify this part of the MATLAB code, which the A-axis, it's a MATLAB command that you will tell it that which range of x-axis and y-axis you are interested in. In this case, for the x minimum x, we want minus 3.03, and the maximum of the x axis as a 3 electron volt. And for the y-axis, we wanted the range from starting from 0 to 7.3 electron volt. So I'm done. Thank you. Is there any question?
Please join me. Thank you, Sarah. So it was a record brief. Thank you. So any questions in the audience, online or in the chat line?
Which transition is below LUMO HOMO? Still there are some peaks.
Excuse me, Dr. King, can you repeat the question? I think Dr. Tupa is far away from microphone.
I still see some peaks below LUMO HOMO transition. What are those peaks?
You mean these peaks for this figure?
Below, yeah, that peak. Yes,
I'm not sure. We need to double check the O strength file and see which transition or correspond to this energy level. So I'm not sure for this case what are each peaks correspond to. I think just these two are kind of more important for us, which was LUMO to HOMO, and this one LUMO plus 2 to HOMO.
Sorry,
So
I think what Dr. Tupa, what Dinesh is asking, just generally, qualitatively, how to interpret presence of optical signal below HOMO-LUMO gap. not literally which individual, but generally, what is it?
Something like, for example, maybe it corresponds to LUMO minus something to HOMO, or so.
So let me reformulate the question. Those transitions below the gap, do they happen from between valence and conduction band? From valence to valence? From conduction to conduction? Or like which of the three options?
Still, I'm not sure about the answer for this question.
Anyone wants to try? We will have several talks to focus. So let's mark this open questions for all of us, and try to get it from each next speaker.
Can I ask why we think the LUMO +2 to HOMO transition is so much more important than them, when the one that like 0.8 EV is like 2 orders of magnitude higher intensity?
Okay, let's maybe Sarah, please prepare to answer a question of David, and I will contribute a little bit to the question of Dinesh.
Okay.
So, and Sarah, would you please go to the editing mode so that one can put a little annotation? Editing, exit the presentation mode and go to the editing mode.
Let's see.
Yeah, thank you. The question that Dinesh did ask is showing a conflict between intuitive thinking and objective calculations. So there is a process that one can agree that we go from higher excited to lower excited by scrolling several orbitals in valence band and conduction band, and then at the end we come to the HOMO-LUMO gap. So the HOMO-LUMO transition between valence and conduction band seems to be to have the lowest transition energy, right?
Yep.
Yes, agree. But we were in this little exercise, we were thinking that the light can be emitted only to ground state from an excited state. But in addition, there are processes of radiative transition between several excited states. So if you go between individual electronic orbitals radiative way, then the transition energies of this little processes will be below the gap. Sarah, would you approve?
Yeah.
Okay, so this question is done. Now let's return to the question by David.
So the question by David, why these two transitions are important. So the LUMO to HOMO is, as Dr. Klein said, I think we expected to have the lowest excitation energy and the highest intensity. So just we wanted to see that if we are right or wrong. So that LUMO to HOMO is for that. But LUMO +2 to HOMO. So for this one, actually, since we have for the in our paper we had a kind of a figure that has all three spin multiplicities on it. So this one is just for the an up-down one or the low spin multiplicity. So on that figure that all three were together. So we just showed this transition. I think we wanted to comparison it with the maybe the other two spin multiplicities. So I think the reason was that because of the comparison, but I'm not sure that if any other reason is there is any other reason for this one or no.
David, are you satisfied with the answer? Sure. Okay, David is happy. Are there more questions to Sarah, either in the room, online, or in chat? Any comments, corrections, expressions of admiration? Okay, questions 1, questions 2, questions 3. Thanks, Sarah, once again.
Thank you.
Very thank you. You were the first to teach us what is photoluminescence. And now we'll go to a little bit more details. Kamrun, thank you for joining. Your project will be to compute photoluminescence for spin polarized objects. So you follow Sarah.
Yeah, sure.
Okay, so the next in the schedule is William. Let me share screen. And now we will go a little slower from the basics to catch on all background.
So here's some stuff about photoluminescence. I try to keep it short and sweet because there's a lot of math and confusing parts behind this topic. So photoluminescence, and the definition of it is that when matter, how light absorbed or emits from it. So absorption is when matter takes in a photon and then an electron is moved from its initial state to a higher energy level. And then spontaneous emission is matter releases a photon from it, and then it drops an electron from a higher energy level to a lower energy level. And then stimulated emission, it's like just our spontaneous emission, but instead of it just happening on its own, we have to then introduce a photon to the system to then it will then drop an electron from a higher to a lower energy level. And we can see here that our photon is labeled as h nu, where or h bar nu, where h bar is h over 2 pi, and nu is our frequency. And then in our last part, we can see that we have a photon going by it, and then we're emitting another photon. Something to notice about in the stimulated emission is that these two photons, they'll have the same direction as each other. Frequency and polarization. And polarization is that it'll have that same wave in, I guess, the same direction to each other. So such that if like you were looking at them side by side, it would be looking like it was like you'd only see one because they'd be perfectly covering the one behind it. And then to Einstein coefficients, they measure how likely a photon will be absorbed or emitted from the atom, where A is our spontaneous emission from going from our level from X and Y. B, that can either represent the absorption or what I should say, the absorption or the stimulated emission, or a spontaneous and accident. Probability from our transition from X to Y. G of X is our degeneracy, which is how many states could be in one level. And then F of XY is our oscillator strength. And then we can see here that from our continuous spectrum, our emission lines, that's like where at a certain frequency, we're going to get a photon out of it. We can see at those frequencies, we're receiving light, which is what we can see. Then later on, then we can see what our absorption lines are. So when our photon absorbed, we're not getting any light back. So that's why we don't have anything. And that's what I have.
Okay, please join me in thanking you. So we've got introduction to spectroscopy. Any questions to you in the audience? Any questions to you from online? Any questions in the chat line?
Or I guess. So you have oscillator strength there. What would, well, I guess what's a good way to describe oscillator strength?
I'm not sure exactly what this oscillator strength is. My initial thought would be, since like we're dealing with is a wave, would be some sort of strength of our photon or something related to that. That's my initial thought.
And what is your good memories of the talk by Joseph last time? Or maybe 2 times ago?
I'm not sure of.
Just ask him, maybe he will help.
Yeah, so the oscillator strength is related directly, like through these constants, basically, to the probability that a photon will undergo that transition. So I guess from Will's equations here, we can see that there's like a few other constants that come into play, or a few other variables, I should say, like the frequency and the degeneracy. But like the main driver of it is the oscillator strength, which measures kind of like an overlap almost between 2 different like states. So if they have a high overlap, they have a high probability of transferring.
And
One thing that I would like to mention that confused me at first is that our E squared is the charge of an electron and not Euler's number squared. That's something that
What?
our E squared is the charge of an electron and not Euler's number, which confused me for a little bit.
Are you satisfied with this team answer? You want? Okay. More questions to Vivian? It was crystal clear. Thank you once again. Stop sharing, and next presenter is Joseph. So we keep wrapping up, and several things related to photoluminescence.
Yeah, so like Dr. Killen said, we're just going to continue talking about photoluminescence. So kind of the main idea here is basically looking at how charge will relax and how the holes, I guess mostly just the excited electron will relax, and the probabilities associated with that. So first we have to worry about when that relaxation is actually going to emit a photon, or radiative recombination. From Will's presentation, we can easily tell that the rate that this will emit is just going to be the Einstein coefficient. And we're just going to relabel that as Kr. And then also here's the equation for the oscillator strength in case you want the equation. To simply just get the value of the oscillator strength, we can run the oscillator strength file, which is the same process we would do when we're calculating the absorption spectrum. And that will give us a big oscillator strength file, which will tell us this number for all combinations of bands that we're concerned about. Here we can also see different rep commands that we can do on that oscillator strength file to get the different oscillator strengths that we might worry about. So we have oscillations between like two excited states or intra-conduction band transitions. Same thing for the valence band transitions. And then we also have interband transitions. So basically going from an excited state to a relaxed state, I guess. And down below, we can see what one line of the oscillator strength file is going to look like. The two values that we're really concerned with are the oscillator strength and the transition energy, which both show up in our calculation of the radiative emission rate. The other pathway that charge can relax is going to be through non-radiative. And the way it will lose energy instead of is through a photon is through a phonon or just heat that gets released into the rest of the system. And this is what we were calculating before when we were calculating the Redfield tensor. And so it will follow the exact same process that we did before, where we'll just use the autocorrelation functions and get the triple R matrix. And that's going to be approximately equal to the non-radiative rate. And just for an example, down below, I did this calculation for one of my models for the HOMO-LUMO transition. And when you run the correlation MATLAB script, the output in the triple R matrix is going to be inverse femtoseconds. In case you need to convert that to anything else. Combining those two rates, we're going to be able to get this photoluminescence quantum yield, which is a lot of words, but basically all it's saying is how many photons are emitted as a fraction of how many photons are absorbed. The big assumption that we make when we're calculating this is called Kasha's rule, which down in the bottom corner is a good kind of explanation of it. We assume that if you have a electron go to a very high excited state far above LUMO, that it will descend to the LUMO state, just releasing phonons, so non-radiatively. And then the only transition that will release a photon is between the LUMO and the HOMO. This doesn't happen all the time, which I'll talk about in a second. But this will greatly simplify this equation over to the left into what it is. If you are concerned about photon emission from higher excited states, this equation will become much more complex. As an example of some of these values, you can see down in the corner that I calculated for a few of my models. The first model has about a 55% quantum yield, so about half of the photons that are excited, or half of the electrons that are excited will release another photon. And as defects are added into it, like COH and SiOC, that quantum yield goes down by quite a bit. So we also have some exceptions to Kasha's rule that we have to worry about. And I basically outlined basically how we would get these exceptions, but basically what it's playing with is if you want to adjust what KR, KN are in order to get emission from a different level. So for example, if you have a bunch of high excited states, even further above LUMO, they'll have a low overlap between LUMO and those higher excited states. So those electrons won't get a chance to fall down to LUMO. And instead, what they might do is basically fall all the way down from a high excited state down to HOMO and release a photon that way. And so through like these two sorts of exceptions, we could get luminescence from different states and different energies than just the HOMO-LUMO gap. So that is something to pay attention to if you have like an odd band energy diagram, I guess. That is what I have so far.
Okay, let's join you. Thanks. Any questions in, okay,
What is a photon?
So the phonon is just a like discrete it's kind of like a photon, except instead of releasing into like space, it's just released into the surrounding atoms as heat. So it'll just vibrate all of the atoms next to it.
So it's really just energy being released.
Yes, into kinetic energy. Yep. Okay.
quantum of sound.
Yeah, that would be a good way to put it.
I will calculate KR.
The K, so KR will be calculated through the Einstein coefficient that we were just talking about with Will before, which will involve the transition energy between these two states and the degeneracy, as well as the oscillator strength. The KNR, so the non-radiative, would be calculated through the non-adiabatic couplings that we were doing and calculated on the Redfield tensor with. And then just looking at the indices of that matrix, that would tell you the rate between those two states.
When it shows when you come to Lumo plus and transition. Why not Lumo minus and?
Like in this example, why I chose the homo-lumo.
At last. Okay, where you are concerned on Lumo plus and will.
Oh, yes. So here what I was trying to show was that the Kasha's rule, we're not always going to get photons only emitted from the homo-lumo transition. We might get photons emitted from a homo to lumo +5 or something like that. So I guess like a good example, a better example is this one off to the right, where the lumo is very close in energy to all of these higher excited states. So if you put a photon up to this higher excited state, and lumo is going to have like a relatively low oscillator strength connection to homo, the KR is going to be low because its oscillator strength will be low. So then we will be about just as likely to see a transition from homo to lumo releasing a photon, as well as like a higher lumo state releasing a photon. Yep.
Questions? Let's check if anyone asks you questions in the chat line.
Yeah, so do you have a question in the chat line? How to assess if Kasha or non-Kasha transitions play a more important role? Can it be done visually? I think that a visual way to do it, other than being able to look at, I think a good first step might be to look at the band energies, kind of like a diagram that I have here. Another good way to do it might be through the emission spectrum, like what Sarah was showing before, where instead of just emitting photons for the homo-lumo transition, we also had different energies that were releasing photons. So I guess you could cross-reference the emission graph with its peaks to the transition energy between different pairings of homo and like lumo plus n.
Is sufficient justification to compute spectra and place them in your next presentation?
I think so.
So more questions to Joseph? One, questions two, questions three. Yeah, question. Very solid, very solid. So next presenter is Keya, and she has a scale concept. So I will try to show her slide, but I cannot compete and present it as a solid talk. I will just focus on a couple of important things. And everyone is welcome to cooperate and be closer. So it will be like not only Keya, but the whole club of computational chemists. So as we have heard from Joseph, it is quite beneficial to follow Sarah and compute photoluminescence spectrum. Those are based on our previous calculations on non-radiative relaxational dynamics. This is important. This is different from absorption spectra because the non-Kasha transitions may involve transitions between excited states. And in order to activate them, we need to populate orbitals that are not populated in the ground state. So we need to explore excited state dynamics as a prerequisite to compute photoluminescence. So one has, well, we all have a little code on the top of the quantum dynamics that just converts these dynamics into photoluminescence spectrum. And the aspect that Case was going to show, and I'll just surface her proxy, is just to focus on a couple of lines of the code that are responsible for this emission spectrum. So here the standard things and the name of the code. I hope very much that next few speakers will cover these aspects in more details and from different points of view. So one of the important things that is needed for computing spectra is to import this 4-master optics file, which to my understanding contains oscillator strengths for all possible pairs of orbitals, including both from occupied to unoccupied, as well as occupied to occupied and unoccupied to unoccupied. And I believe on one of the previous talks, previous weeks, David was giving comment about structure and location of this file. Okay. So upon the dynamics is done, the data for occupations of the orbitals in the valence band and conduction band need to be merged with oscillator strengths in the right way. So here are a couple of lines of the code that do implement the equation on the top. So there were a lot of very important key concepts that Joseph has and contributed to us. But there is one keyword that was implicit but not verbalized. When William was showing his diagrams with little levels, dots, and wavy lines, there was naturally assumed that emission happens from exciting to ground, when population goes from higher energy level to lower energy level. If we believe in Boltzmann distribution, if we believe in thermodynamics and thermodynamic equilibrium, this should never happen. All occupations should go to the ground state, right? So the prerequisite for emission is in conflict with equilibrium thermodynamics. It should be a non-equilibrium state. So in the regular stable thermodynamic equilibrium state, the populations are falling, what's the right word for freshman chemistry? Pauli, when all Fermi Pauli exclusion principle, like up to Fermi level, everything is occupied, above everything is empty, right? And now we need to violate this rule. we need to promote an electron higher up. We need to have a non-equilibrium. We need to have populations that are opposite to this natural arrangement of things. So it should be inverted. And the keyword is population inversion. So prerequisite for photoluminescence is population inversion. And we may set up scanning of the pairs of orbitals in such way so that we have one is always more senior than the other, to know who is senior, who is junior between orbitals. And then we can look if we ever have population. So let's look on the green box. If you have population of the higher orbital bigger than population of a lower orbital. So if the subtraction is positive, it means we observe population inversion. If it is negative, then we already arrange summation in such way that it will not be negative. We count only possible contributions. So this little box bracket is population inversion. Shows. Okay, another prerequisite for photoluminescence is that it should match the emitted photon matching energy difference between initial and final states. So the frequency of emitted photon is equals to energy difference between initial and final. And the third prerequisite is that emitting pair of states should have non-zero oscillator strength, should have non-zero transition dipole, and should be able to contribute. And then we scan over all the things. So populations are time dependent. Therefore, as we run through quantum dynamics, there are different pairs of orbitals that contribute or not contribute to the emission. And in this slide code, we have time dependent populations. We have the energy differences, and we have the oscillator strength that depends on two indices. When all these factors are combined, just basically multiplied, we implement resonance condition. Instead of delta function, we have Gaussian function, exponential, and the scanning over all possible emission frequencies is arranged as a contribution over all possible transitions is arranged as summation of different terms of this thing. So the resulting variable slice is a probability to emit a quantum at certain wavelengths at certain time. And if we scan through all possible time steps of our quantum dynamics, we will see that at each time slice, these probabilities as function of frequency are different, right? So if we accumulate data into this array by adding more and more rows each time it comes through the cycle, it will be a matrix. And a little forward to be a little less abstract, more practical. So the emission for certain systems can be even more pronounced of these non-Kasha transitions. You will get that Dinesh was asking. But the experiments that track time dependence of emission are cool and needed, but they are like 10, 100 times more expensive. Much more typical ways to look on just whether it emits or not. So fluorimeters are much like one can even buy it into a household. It's not more expensive than an average car. So one can integrate all these emission events over timeline and have this integrated emission. Let's go back to the line to code. So we do have this emission thing. One could make just summation along each line of this matrix, but since we have the time steps have different duration, one needs to arrange the varying increment of time into this integration. But as soon as this little convolution of two matrices is done, you have time-dependent emission. Another thing which is often shown doesn't have any relation to practical observables, but it does appeal to intuitive human thinking. So if we forget about this strange things about from non-Kasha emission, below gap emission, and just follow how the excited states of different energy cascading from more excited to lower excited. We can model this process just by arranging this population of electrons, population of holes, and the resonance condition, and just illustrate so that initial excitation at certain wavelengths, certain energy changes over time and drops to the homo dynamics of excited state. Again, it is not an experimental observable. It is not anything we compare. It's only a way to interpret how things are arranged. Okay. And practically, while studying certain materials, we may want to redo this calculation again and again with different initial conditions, because the emission properties do depend on excitation energy. Let's see if here shows the here things together. Okay, the presentation is done. You can skip upload since the presenter is not with on the meeting. But any questions, please go ahead and ask questions, and I'll either try to address them or we will postpone until he joins us next meeting and answer more questions. Yes,
Just say one more time on this slide, I guess, what the P is.
this one that is right now.
Like what it all equals. Is that like the power, the intensity?
Well, but is here for excited state to appear at certain transition energy at a certain time. So in the code, it is encoded based on the name of one of my postdoctoral advisors. Either, I don't know, as a making fun of him or as a make a tribute to him. But it is not observable. It's only a way to visualize. Question? Any questions from online attendees? Any questions from the chat line? Okay, if there are no questions, let's go to the next presenter. So next speaker is Amara. Amara, would you like to share screen? And
Yes, sure.
yeah, thank you.
Can you enable me?
We can hear you.
I can't share my screen.
Oh, you cannot. Let me. Okay, let's try now.
Okay. So hello everyone. I think everything is explained by Professor before, so I will explain the same thing. And the most important thing is that exciton, that in this case we study the dynamic of the exciton, that is the electron hole pair, and we need all the input files that we used for in the previous meeting. And here is the summary of that input files, and there are the 5 input files, and the RRR file, energy pop file, master optic file, band out file, and the MATLAB code. And we need to make sure that all the files have the same same number of lines. So we use in the same folder with the MATLAB code, and then we need open the MATLAB code, and we need to make some changes in the input parameters. So these are the some parameters that we need to change: time step, min, and Omax, and the HOMO, and then the Z step that we can calculate from, that we can see from the band out file, and then the Z size from the postcard file. So these are the input parameters that we need to change, and this is the code that can be used to calculate the time integrated emission. And these are the equations that are explained by the professor, in which we use the one is time resolved emission and one is time integrated emission. So this is my model that I use for this calculation, that is the CNT with some defect, and that is the normal relaxation with initial condition, in which the yellow line represent the charge density of the photoexcited electron, and the dotted line represent the average energy of electron. And then this is the simple excitation of the excitation energy, how it changed with the time scale. So it is dynamic of the exciton energy dissipation with time, and the color range from the red to the blue, and red is the maximum population and blue is the zero population. And if it is the yellow, so it's mean it is in between the range. And this is the emission, time resolved emission spectra, and this is the time integrated spectra. So we calculate the time resolved emission in the excited state, that is based on the presence of inverse occupation along the excited state trajectory and intensity of the oscillator strength. And the time integration is just simply the time resolved emission along the trajectory. So these are the results. That's it from my side. If you have any question, feel free to ask.
Okay, please join me in taking a part. So any questions or suggestions? Like as a practical manual, is it clear? Everyone of us can repeat it. Amara, I do have a couple of suggestions rather than questions.
Okay.
So for this figure, would you be able to learn from Joseph and give a number? What is the photoluminescence quantum yield for this model?
For this figure?
Yes. It's not available right as a number from this code. You need additional code that Joseph presented today.
Okay, maybe I missed that code, so I will go through that.
His presentation, maybe listen to the recording and try to find quantum yield.
Okay, yes.
Let's go to the previous figure. Maybe Dr. Hunt has questions to it. So from either fundamental or practical side. So while we are still thinking if there are more questions, let briefly, there are specific features of the geometry of your model. So can you please bring your marker your cursor to the defect, to the small to this absorbed to the surface. Closer to the molecule on the model. Yes. So,
Yes.
so there are two carbon-carbon bonds that define this model, right?
Yes.
So right now, these two bonds are arranged in parallel to the tube axis.
Yes.
Would you be able to place them perpendicular to the tube axis or at some other different angle?
Yes.
Okay, yeah, so it would be of very big scientific interest to change the orientation of the attachment points and see how the spectra and quantum yield will change.
Okay. Yes.
So it was not a question, it was just suggestion how to.
Yes.
Any additional questions to Amara? Let's count down. Questions 1, questions 2, questions 3. Please join me in thanking Amara when she came. Okay, let me ask Adam and London, would you like to share something, or you would prefer to postpone to the next meeting?
I guess I don't know that I really have anything to share that you didn't already cover with Keya's presentation, because that was basically what I was going to talk about, was the, that equation itself and how it gets implemented in the code. And you already did a pretty good job with that.
Great. Thank you. Thank you for the compliment. Do you have any slides to share and discuss?
I do not have any slides, no.
Okay, then let's postpone it to the next time. Adam, would you like to share anything, or you are happy without it?
Yeah, generally same boat as Landon, but I can share my slides. Sure, it's nothing I don't think we've already.
So if you have slides, please share. If you give us some discussion, like crystallization center to discuss things.
Sure. Yeah.
Thank you.
Okay. So I was just going to talk about time dependent, time resolved, and time integrated. I found these cool figures that basically show we're taking slices of time dependent emission spectra, certain wavelengths, integrating those to just this time resolved spectrum over here. I just showed the part of the code, I guess, that does this and what it relates to. Yeah, that's basically what I have for that. It's nothing we haven't already talked about, but also I found this, while I was doing research, I found this time slicing that they do. So they basically just overlay these emission spectra over one another at different times, and they do this for. They actually plot another figure from this. Basically, it says like how the intensity, I guess, changes over time. But they use this to explore like solvent relaxation. Now that affects the rate of these things and I guess charge transfer systems. So they looked at an intermolecular charge transfer system here, and they just looked at it all these different time slices. But that was basically all I had.
Okay, is it time to upload to Adam, right? Okay, let's take any questions in the room? Any questions from online audience? Adam, do you see any questions in the chat line?
Oh, yeah. Absolutely, yeah. Okay. Yeah, fluorescence, phosphorescence, and photoluminescence. Photoluminescence describes fluorescence, phosphorescence, and that resonant photoluminescence that I think William described here. They're not equal. They're describing different processes. These are like slow releases. I guess they're not releases, but slow decays. Phosphorescence specifically describes entering or a decay from a triplet state, so that usually takes a bit longer. And so the emitted, I guess, wavelength of light is going to be a little bit longer than with fluorescence.
So fireflies, which sort of emission do they show?
I believe it's phosphorescence because it's so long-lived.
Okay. Can anyone compute phosphorescence without spin orbit coupling? Oh, let's make a vote. Who can compute phosphorescence without computationally without involving spin orbit coupling? I don't. No one is raising hands, which means it's likely impossible.
Yeah.
So if you go to connection to the next speaker, David, who will show that spin orbit coupling is more universal and will enable both fluorescence and phosphorescence if needed. Just I wouldn't say personal, practical question. Did you got couplings? Did you got input files to run this photoluminescence codes for your model? Or there are some technical difficulties?
I did get figures for it. I didn't see very much from them. If it runs, I'll show you.
Okay.
Okay, yeah. So
I think one needs to push space or any key once again.
let's see.
So how do you interpret that TM is changing over time? You see this TM is raising in your command line.
Yeah, those are just the. Okay, so here we have it.
Ah, so you have everything, right?
I believe so, yeah.
So you have computed emission.
Yeah.
Okay, that's then a great talk with a practical component. You are just ready to combine these figures, describe them, and go to the next paper.
Maybe so. Maybe a bit more work, but
okay, I'm very happy to see it. Any questions to this little results? It looks like Homo emission is noticeable, right? So let's well, very soon, starting from the next week, we'll go to research updates. So probably this is already partially belongs to research update, but any questions to the protocol? Anyone wants to learn from Adam how to run, how to compute photoluminescence? Questions. Please join me in thanking Adam once again. Really impressive. I was always wishing to see the emission of porphyrites in computation. Good. Adam, if you do not have questions to yourself or to the audience, you can stop sharing. Oh, nice to see you, Aaron. And last but not least, one more presentation by David. And basically, he will be the last speaker, but he will cover two other subjects, two other ways to look on the photoluminescence. One is how to do the same things as previous speakers were explaining, not only spin polarization, as Sarah presented, but with spin orbit coupling, which enables phosphorescence if needed. And the third part of his today's knowledgeable presentation will be about assessing the line width of any emission signal. Okay, floor is yours.
So I am going to talk about two more things that we can observables we can examine in our calculations. So MDPL, which is the molecular dynamics photoluminescence, and photoluminescence quantum yield. So we're going to start with MDPL. So if we, with your spin orbit calculation, there is a code that is in the bin on NERSC, which is modified from coding off human. So it's this OS_PL_ script. You're also going to need from your coupling calculations all the OS_strength_VC.xxx files. So these are your files that show the oscillator strength along their trajectory, and specifically the ones along for interband. So if we open up this OS_PL script, you're going to see what we have over here. And if you look in the red box, I have the values. These are the values of X in the oscillator strength files that you have. So however many you have, you should fill in here. Depending on what V script you use, you may also have to change this 4 in the %04G to 3, because that's setting it out to be 4 digits. And I think I'm the only one that uses code that sets it to 4 digits. So what this code does is it generates an oscillator strength file with just the homolumal transition through all of along your molecular dynamics trajectory. So to actually generate this spectra, once you have that oscillator strength file that was generated by the script in the last slide, you treat it just like how we treat absorption spectra. So you will plot it and you will get out a plot, which I did not include. I can probably add one quick.
Yeah, let's do it. In the same style as Adam. So I will cancel the session.
So if you look at this, this is the MDPL for a few of my structures that I used on my Sanibel poster. So if we look at them, part of the reason we're interested in this is it allows us to calculate the width of these so we can compare them to experimental spectra. So then moving on to the photoluminescence quantum yield, we have a MATLAB script that I wrote to calculate the photoluminescence quantum yield for spin orbit coupling. I wrote this based on some Excel sheets that Aaron sent me. So you need the energy pop, 4-master optics, and the RRR file. And then if you run this, it will calculate the PLQY based on the Redfield tensor and the Einstein coefficient of spontaneous emission. The major thing you would have to change probably these first three. Realistically, the two Gs are going to be the same, but if you had a system that would require changing them, you would change it here. So this outputs these photoluminescent quantum yield values. So for this code, we use the average value for the near degenerate band gap transitions as our photoluminescence quantum yield, which is why we have 4 values here and then a final value. So we calculated for HOMO to LUMO plus 1, HOMO minus 1 to LUMO, HOMO minus 1 to LUMO plus 1. And then take the average of that value. And that's the end of my presentation.
Okay, please join me in thank you. Any questions in the room? How did you find the difference?
So you need to examine if there's any degenerate states in your file. So due to the spin orbit, we basically end up with 2 degenerate states.
So what that file would just look like you have repeat lines,
What do you mean?
or like, you said you can look at the file, it's also it's degenerate, like would you just see?
Do you insert degeneracy manually or it automatically assess if any energy levels close enough?
We can insert it, it's a variable we insert. So it's based on the value of energy and whether they're the same or pretty much the same. So all my values are less than 1 million electron volts difference. Or some of them significantly less than 1 million electron volts.
If one needs to compute photoluminescence not by MTPL but by Redfield approach, same as Sarah, Keya, Amara, are there any changes to the code, or you just modify the input parameters and use the same code? What do you mean? If you need to not keep width, but if you just need the photoluminescence, which you are not showing in this talk, not a quantum yield.
Oh, like the blue figures?
Yes. Does the way to compute blue figures similar but different from situation with singletons?
Virtually identical.
Therefore, you skip it.
Yeah, basically.
Okay.
This is just from one of the other figures. It's it's virtually identical.
Okay, yeah, thank you. Okay. Let's check. Let's check if anyone asks you questions in the chat line. And Adam, please look at this question and think how you would answer it.
Aaron asks, is MDPL able to capture Frank Condon factors vibrational progressions?
It is a provocative question.
I hope so.
Let's give chance to Adam. Adam, would you like to just share your opinion to address this question?
Ooh, I don't know.
I know it's a little too steep step to listen for new methods 4 minutes ago and now assess it and compare. But just your vision, how would this MTPL method do anything comparable to Frank Condon progression or very far, or do you see any connections? You see nothing, you can criticize that it is partial, just
Yeah, I kind of can. Just with, I don't know exactly how to put it, but you have, the energy.
So what's the main condition to develop from quantum progression? And maybe you can even briefly remind it to those of us who want such a refresher. Like, how does one come to from quantum progression? Which conditions to nuclear degrees of freedom are imposed?
Vibrational states.
So vibrational, which means vibrations, interatomic distances, are they just point charges or something more than that?
I mean, there's something more than that.
Like you already answered, sorry for making it as a little looking like exam, but you once answered one needs vibrational state. So instead of continuous exploration of different points on the potential energy surface, you're speaking of vibrational states.
Yeah.
So,
Like of the, of the entire molecule, or of portions.
So vibrational motion should be classical or quantum in order to speak about from quantum factors.
Probably quantum.
Perfect. Yeah, thank you. And what do you think about, do not hesitate to be critical. What do you think about the MTPL method that David has presented? Does it have any quantization of positions of ions?
Not that I can see, no.
Like when we run molecular dynamics in computational chemistry software, do you have strict exact position of ions, or they all atoms are like cloud which is smeared over the whole space?
I believe they're clouds that just just gives them electronic structure, bases their motion on that.
Okay, thank you. David, would you like to continue this discussion and summarize? You have all information and I have no doubts. You know that, right? Only a little exercise to verbalize things. Put it into words.
So I think that's most of the reason we were doing MDPL, wasn't it? Because we wanted to, because we need to worry about it over the trajectory instead of just at a random fixed point that we picked or get picked.
Yes. So right now we are approaching to the real life and potential interaction with reviewers of works that we do. So David is presenting situation from a constructive point of view, achieving good result. So in order to see how atomistic motion affects line width, this method is introduced. But if reviewers are trained to find any weaknesses, they will immediately tell any discussion of quantum factors is based on quantization of nuclear motion. If your nuclear motion is not quantized, it is not from quantum factor. And it will look like we are silly and stupid, and they are right. So one needs to find what Aaron invites us to do is to find, he gives us a task to find a bridge, to find a connection, to say that on one hand we appreciate and that if nuclear degrees of freedom are quantized, there is a progression that contributes to width of a line. On another hand, we can approximately get the same effect by scanning through whole amplitude of interatomic motions. Is it something what you wanted to say?
Yeah.
Aaron, would you like to summarize in a better way? Did we perform a good try answering your question, and how would you answer yourself?
I guess I would hedge and say it captures some aspects that you would see with Frank Condon,
Okay.
and that we're dealing with solids and high temperatures. So it's experimentally, those wouldn't be resolvable anyway, unless you were doing very specific types of or very specific experiments, like low temperature or something. So it could be like a homogeneous line width.
Many thanks, many thanks. So let me illustrate this discussion, and I think Adam will agree and appreciate it. So the Frank Condon progression, which Adam did compute in his course term, shows that either charge transfer or optical transitions do depend on energy offset and have a progression of peaks when vibrational levels come of the initial and final state come into literal resonance. Adam, would you confirm that this figure looks similar to what you did in the past?
Yeah, it does. It looks like one of the figures.
Okay, thank you. And if one increases temperature, then through several mechanisms, the width of each individual peak will become broader, and several peaks originating from quantized nature of nuclear motion will start overlapping. So as temperature will increase, the system is coming to like quasi-classical regime, and the modeling of transitions with an account of this variety of transitions through classical mechanism will coincide better and better with quantum approach through Frank Condon progression. Aaron, would you take it as an improvement on our side?
I mean, I would buy it.
Okay, thank you. David, what do you think about another comment from Aaron?
Other aspect that is needed for Frank Condon is excited state potential energy surface here is only ground state. I would agree on both points.
Okay. So, any additional questions to David from the audience, from online audience, or from the chat line? Questions 1, questions 2, questions 3. Please join me in thanking David, all participants and presenters. So from now on, you